Hey guys, it's Malta here, and before we get into today's video, I just want to apologize for being away for the better part of a month. I've been very busy with completing college applications and scholarships, along with competing in tennis tournaments. It was definitely good to be back. Now in today's video, we're going to conclude our learning regarding infinite limits by determining one-sided limits. These problems will incorporate a wide range of strategies that we have learned from the previous sections, and there will be many similarities to the one-sided limit section that we previously covered. So without any further ado, let's get into it. So the first question that we have here, it's just asking us to find the one-sided limit. And so the problem that we have, it's number 33, it's asking us the limit as x goes to -1 from the right of 1 over x plus 1. And so what we want to do is, I want to start off by just doing some simple, plug and chug. And what that means is all we're going to do is we're going to use the value of our limit, what our limit's going to -1, and we're just going to replace it for our variable x to see if we'll actually get an answer for our limit. So let's go ahead and do that. So the first thing that we have here is we're going to have the limit as x goes to -1 from the right, and then what we're going to say is this is 1 over, then in parentheses -1, because we're going to replace x with -1 plus 1. Now as you can see, this is already looking a little bit problematic because this simplifies down to 1 over 0. And this is an issue because whenever we have division by 0, that leads to a result that is undefined. And undefined is not going to be a suitable answer to this limit. So instead what we're going to have to do is, we're going to instead plug in values for x, for this variable x, that are close to -1 to the right. And so what that means is we're going to look at values that are going to be slightly greater than -1. So the first value that I want to select is x equals -0.9. And so in doing this, what we're just going to do is we're going to carry out our same operation as we did previously. So we're going to get the limit as x goes to -1 from the right of 1 over this should have actually been a negative here, my bad. -0.9 plus 1. And so what's going to happen here is this is going to give us a result of 1 over 0.1, which is equal to 10. So now this is our first value that we've gotten, but we're going to have to keep getting closer and closer to -1 in order to determine if there's some sort of correlation or some sort of effect that we can determine from getting closer and closer and to try and figure out this one-sided limit. So the next value that we're going to test with is x equals -0.99. So this is going to be the limit as x goes to -1 again from the right of 1 over -0.99 plus 1, which gives us a result of 1 over 0.01, and this is equal to 100. So as you can see, just from going from -0.9 to -0.99, we've increased by a factor of 10 from 10 to 100. So now what we're going to do is we can't really draw a definite conclusion from just two x variables. We're going to need a third x variable to determine exactly where this one-sided limit is going. So for that, what we're going to do is we're going to say x equals -0.999. So this yields a result of the limit as x goes to -1 from the right being 1 over -0.999 plus 1, which ends up giving us 1 over 0.001. And this right here simplifies down to 1,000. So as you can see, once again, we've increased by a factor of 10. Now looking back on it, as you can see, each time that we increase, our decimal value and add another 9, we're increasing by a factor of 10. And from the looks of this, from the looks of these 3 data points and the changes that we've seen, we can pretty much determine here that we're going to a limit that's going to be at infinity because we are increasing without bound. So what we're going to say for this problem is that the limit as x goes to 1, or I should say as x goes to -1 from the right of 1 over x plus 1 is equal to infinity because we're increasing without bound, and from the looks of it, we are going to go to infinity. Alright, so now we have this next question here. This is problem number 34. And in 34, we have the limit as x goes to 1 from the left of negative 1 over x minus 1 squared. And so for this problem, what we're going to do is we're going to start off as we did in the last one. And we're just going to try substituting in the value of our limit. So for this, what we're going to have is we have the limit as x goes to 1 from the left of negative 1 over, then parentheses, 1 minus 1 squared. So this simplifies down to negative 1 over 0, which is, once again, problematic because whenever we divide by 0, we end up with a result that's undefined, and that's not going to cut it. We need to find another alternative method to solving this. So once again, like with our last question, we're going to try plugging in numbers that are close to 1 but are slightly less than it. So to start off with, what we're going to do is we're going to try x equals 0.9 because it's slightly less than 1. So what we're going to have here is we have the limit as x goes to 1 from the left of, I should make this 1 a little bigger there, 1 from the left of negative 1 all over 0.9 in parentheses minus 1 squared. So if we do this, we end up getting is we get a result of negative 1 over, let me check here, 0.01. So this in turn gives us and simplifies down to negative 100. Alright, so this is our first data point that we've completed. Now what we gotta do is we have to fill out our next data point. So our next one here is going to be at x equals 0.99. So you can see we're getting closer and closer to 1. But we're not going to be able to get there because if we do go directly to 1, we're going to get an undefined result. So we're going to try and get there as close as we can. So now what we have is we have the limit as x goes to 1 from the left of negative 1 all over, parentheses again, 0.99 minus 1 squared, which gives us negative 1 over 0.0001, which is pretty small, like this, and this in turn gives us a result of negative 10,000. So there we go. So you can see we are getting to some pretty large negative values. So now what we're going to do though is we only have 2 data points entered. We need a third one in order to draw a definite conclusion. So our third data point is going to be x equals, just like this, x equals 0.999. So we're going to get the limit as x goes to 1 from the left of negative 1 all over, in parentheses 0.999 minus 1, and then we're going to square all that. This is going to give us a result of negative 1 over 0.0000, I should say, 1. So we're going to have 5 zeros out to the right of the decimal. And so what this ends up giving us, and simplifying down to, is a result of negative 1 million. So obviously we're looking at some pretty big numbers here. I should say pretty small because they are very negative. So there you go. So in turn, what we can see here obviously is that as we continue to get closer and closer to 1 from the left, we keep getting a result that is more and more negative. And so what this leads us to is the conclusion that we are decreasing without bound, which in turn means that this limit of x going to 1 from the left of negative 1 all over x minus 1 squared is indeed equal to negative infinity, because we are decreasing without bound. So alright, there we go with that question. That one was pretty similar, I must admit, to the previous one, but these next ones are going to be definitely far different. So here you go. So in problem number 35, looking at the limit as x goes to 2 to the right of x over x minus 2. And so in this case, what we're going to do is we're going to start off again by just plugging in this limit variable. So we're going to get the limit as x goes to 2 from the right of 2, because we're just going to replace x, and then we're going to get 2 minus 2. And as you can see, we have problems already because this is 2 over 0, which is undefined. So that's a bit of a problem. But now what we're going to do is we're going to try plugging in some other values in order to try to determine an answer. So first value that we're going to look at is x equals 2.1. So here's x equals 2.1. We're just going to do this plug-in. So we have the limit as x goes to 2 from the right, which is going to be 2.1 all over 2.1 minus 2, which is great because we get 2.1 all over 0.1. And this in turn simplifies and gives us a result of 21. But 21 in and of itself is not that useful. We have to determine some other results as well. So we're going to look this time now at x equals 2.01, because that's even closer to 2 and a little bit greater than it. So then we're going to have the limit as x goes to 2.01 from the right. I messed this up. This should just be the limit as x goes to 2 to the right, which is going to be, in this case, 2.01 all over 2.01 minus 2. So we end up getting 2.01 all over 0.01. And in this situation, we're going to go from 21 to 201. Okay, so as you can see, we've gotten a value that's much bigger than 21 now, but we're still going to have to add another data point to our entry here. So now our next one is going to be x equals 2.001. So we're going to get the limit as x goes to 2 from the right of 2.001 all over 2.001 minus 2, which is 2.001 all over 0.001, which is 2001. So there we go. We went from 21 to 201 to 2001, and as a result it looks like we're increasing without bound. So what we can say here is that this limit as x goes to 2 from the right, oh that's sloppy, of x over x minus 2 is in fact going to end up with a result of infinity, because we're, simply put, increasing without bound. Alright, so here we go. We have number 36 this time. In 36, we're looking at the limit as x goes to 2, but this time from the left, of x squared all over x squared plus 4. So in this case, we're going to just do our simple initial step of just plugging in the limit value into our limit and replacing the x variable with that limit value. So we're just going to get the limit as x goes to 2 from the left of 2 squared all over 2 squared plus 4, and this in turn gives us a result of 4 over, would you look at that, 8, which is 1/2. And this is a great example of why you always want to start off by substituting in the limit value for your variable, because as you can see here, although in our previous 3 examples doing that first step accomplished absolutely nothing, we saved ourselves a ton of time because we were just able to easily determine this limit just because you could directly substitute in the limit value. So this right here, this limit, is equal to 1/2, as you can clearly see right here. So there you go. So 36 is definitely one of the easier ones. So in 37 now, we're looking at the limit as x goes to -3 from the left of x plus 3 all over x squared plus x minus 6. So once again, we're going to initially start in by plugging in our limit value. So we're going to get the limit as x goes to -3 to the left of -3 plus 3 all over -3 squared plus -3 and then minus 6. Alright, so once we work our way through this problem and do all this simplification, we're going to get 0 here over 0. And that's unfortunate because division by 0 produces a result that's undefined. So obviously we're going to have to try a new method for figuring this one out. So instead what we're going to do is we're actually going to try some simplification. And the way we're going to do the simplification is we're going to say that x plus 3 over x squared plus x minus 6 is indeed equal to x plus 3 all over, believe it or not, this x squared plus x minus 6 simplifies down to x plus 3 times x minus 2. And this is wonderful because look, numerator and denominator have shared terms. As a result, they go bye-bye and they leave. As you can see, we're just left with 1 over x minus 2. And now we have a very, very solvable limit. So all that we got to say now is the limit as x goes to negative 3 from the left is really just 1 over x minus 2. That's all we're looking at. So if we then do direct substitution now, we're going to get 1 over negative 3 minus 2. And would you believe that? We get 1 over negative 5, which is, well, just negative 1/5. And so that's the answer to our limit. So as you can tell, you're going to have to remember those old tools that we use for evaluating limits, because simplification here is just immensely helpful in actually solving this problem. Alright, so now we'll move on to question number 38. So in 38, we're looking at the limit as x goes to negative 1/2, and we're looking at it to the right of it, of 6x squared plus x minus 1 all over 4x squared minus 4x minus 3. So in this question, what we're going to do is, once again, we're just going to plug in our limit value. So we're going to have the limit as x goes to negative 1 over 2 from the right. It's really kind of strange, I must admit, how they put this negative 1/2 in parentheses. You don't see that often. But in any event, we'll just roll with it. So we're going to have 6 times negative 1/2, which is being squared. That's the only part that's being squared. Plus parentheses negative 1/2, then minus 1 all over 4 times negative 1/2, and this value right here is squared, minus 4 times negative 1/2. Dang, this is a mess of numbers. Minus 3. Alright, so there we go. Now we've got it all down on paper, and if we simplify this, I'm not going to write out all the work. I'll just tell you the result. We're just going to skip to the ending. You'll get 0 over 0. And that's kind of fascinating again, because that's just undefined. We cannot divide by 0. But that's not very nice, because now we're going to have to do some more work with this question, which I don't want to have to do. But as we did before, we can simplify this by just some simple factoring. So what we can say now is that this 6x squared plus x minus 1 all over 4x squared minus 4x minus 3 is indeed equal to, just by some simple factoring you can get this result, it's equal to 2x plus 1 times 3x minus 1 over, this is being multiplied, this is being divided by 2x plus 1 in parentheses times 2x minus 3. And this, as with previously, is very, very good, because look, right here, shared terms, these can just leave us. They're gone. We don't need them anymore. So we're just left with 3x minus 1 over 2x minus 3. So in essence now, we're going to have our new limit that we're going to construct, which is really just looking at the limit as x goes to negative 1/2 to the right of 3x minus 1 in parentheses all over 2x minus 3. And so now, because of simplification, we've made this thing a lot more easy to handle, and we can actually now easily figure it out. So what we're going to do is we're going to do our direct substitution in for this one. So what's going to end up happening is we're going to get, I'll put the parentheses here, 3 times negative 1/2, like so, minus 1, okay, all over 2, oops, it's a mess, 2 times negative 1/2 minus 3. We're going to close off the parentheses there, and this in turn is going to end up giving us a result of negative 5/2 in the numerator. So we're going to put this in parentheses. It's making a complex fraction here. all over negative 4, which if we simplify this down, we're going to end up with a limit equaling 5 over 8. So the limit, this limit that we started with, this limit as x goes to negative 1/2 from the right of 6x squared plus x minus 1 all over 4x squared minus 4x minus 3 gives us a final result of 5/8 after we did all that simplification and then we resubstituted in the negative 1/2. So there you go. Alright, so now we have our next question here, and we're looking at problem number 39. And with 39, looking at the limit as x goes to 0 to the left of 1 over, or I should say 1 plus 1 over x. Got a little bit ahead of myself there. So we're going to try our direct substitution again. So we're just going to get the limit as x goes to 0 from the left of 1 plus 1 over 0 in parentheses because we were replacing it for the variable. And well, that's not very nice because 1 over 0 is undefined. So we are looking at undefined right now, but we do have a means to figure this thing out. So what we're going to do is we're going to try ourselves with a value of x equals negative 0.1 because that is just slightly less than 0, and we're looking at 0 to the left. So we're looking at values that are going to be less than 0, and negative 0.1 is less than 0. Alright, so here we go. So we're going to get the limit as x goes to 0 from the left of 1 plus 1 over negative 0.1. And then we'll close this off, which is in fact, once you do all this simplification, equal to negative 9, which it's a bit of an odd result, but negative 9 it is. So now though, we're going to have to keep trying to get closer and closer to the 0 value. So now we're going to do negative 0.01. So we're going to get the limit as x goes to 0 from the left of parentheses 1 plus 1 over negative 0.01, which is equal to, in this case, a result of negative 99. So alright, increased by, or I should say we've decreased actually by a factor of 11, but we're not done yet. We need a third data point in our system. So this time we're going to go with x equals negative 0.001. So we're going to get the limit as x goes to 0 to the left, like this, of parentheses 1 plus 1 over negative 0.001. I'll expand that, I guess, fraction bar. Close the parentheses. And this right here is equal to negative 999. So there we go. Now looking at this, you might say, well, all that's happened is we went from, increased, or should say decreased by a factor of 11 both times. That would be true. But as you can tell, there's obviously no real indication that we're going to stop decreasing by a factor of 11. And so as a result, we're going to end up saying that we are decreasing without bound with this limit. And so that means that in the end, we're going to have this limit here that I'll rewrite, limit as x goes to 0 to the left of 1 plus 1 over x is going to equal negative infinity just because of the fact that we are decreasing without bound. So we have to say that we're going to go to negative infinity. Alright, now we have question number 40. And 40 is a little bit of an interesting one here. It's relating with the limit as x goes to 0, but this time to the right of 6 minus 1 over x cubed. So with this one, we're going to initially do our direct substitution. So we'll get the limit as x goes to 0 to the right of 6 minus 1 over 0 cubed. And once again, this problem kind of ended before it started because look, we're dividing by 1 over 0, and that's obviously going to be a bit of an issue. So we end up with a result of undefined, at this point at least. But now what we're going to have to do is we're going to have to do more substitution in order to try and get a finalized result. So now what we're going to say is we're going to plug in, this time, x equals 0.1, because that is slightly greater than 0. So we're going to get the limit as x goes to 0 from the right of parentheses 6 minus 1 over 0.1 cubed, which this, in turn, what we're going to say from this one is that we're going to get and I will do the work for this one, I will say. We're going to get 6 minus 1000, which is going to lead to a final result of negative 994. So there we go. That's our starting point, at least. Now we're going to do another test. We're going to do another variable that we were going to substitute in. And this one, in this case, is going to be x equals 0.01. And we're going to get the limit as x goes to 0 from the right of, then in parentheses, 6 minus 1 over 0.01 cubed. And in this case, we're going to once again end up with 6 minus, and we're going to end up with subtracting 6 minus a million. So, as you can see, 6 is kind of getting obliterated here. And I'll put in some parentheses just to make this a little clearer. So there you go. And this right here gives us a result of negative 999,994. Now, at this point, what I would say honestly is that we don't really need to test a third variable, a third data point, because look, I mean, we are already so negative. I mean, we were almost at negative 1 million. Obviously, common sense would tell you that we are decreasing without bound here. I mean, there's no way in heck that you can make the argument that, it looks like, this will eventually stop decreasing at such a high rate. It just doesn't look like it's going to. So what we will say from this question is that we're decreasing without bound, and then as a result, we're going to get a finalized answer that the limit as x goes to 0 from the right of 6 minus 1 over x cubed is, for all intensive purposes, equal to negative infinity. And there you go. That's just simply because we are decreasing without bound. So there you go. Well, alright, thanks for tuning into this episode. I hope you enjoyed this lesson, because in the next lesson that we're going to be doing, we're going to be finishing up this section, and we're going to be covering 6 problems that are related to this same topic, but are going to incorporate trigonometric values. And so I think this would be a good place to end, just because we've already been going for a long time. And plus, in our next section, we're going to be looking at things from a little bit different lens, with sine, cosine, tangent, cosecant, secant, and cotangent, which are, of course, in and of themselves, very different from these sort of basic numbers that we've been dealing with presently. So, once again, thank you for watching. If you liked the video, be sure to give it a like, and if you'd like to see more content like this, I would definitely suggest subscribing. So once again, thanks for watching, and I can't wait to see you in our next